So, calculate the momentum as seen by a stationary observer provided to a rocket ship with a rest mass of 1,000 kilograms as it goes from rest up to a speed of 0.99 times the speed of light. Assume Gedanken conditions exist in this example. Okay, so to work out our momentum as seen by a stationary observer, remember our relativistic momentum, oh, I'm not going to do that, I should do it on my thing, that was the point of this. Hang on. Pen. Okay, so our momentum, remember, is equal to our Lorentz factor multiplied by mass multiplied by velocity. So some of these are easy. Mass, we know what mass is. Mass is 1,000. Velocity is 99% of the speed of light. So 0.99, we'll work that out afterwards. Now we need to work out what our gamma value is. So our gamma value is 1 over the square root of 1 minus v squared over c squared. So we need to put in some values for this. So let's have a look. So 0.99 times 3 times 10 to the power of 8. Okay, so 0.99c, that gives us 2.97 times 10 to the 8 as our velocity. Okay, let's put that over here as well. 2.97 times 10 to the 8. So if we just take the speed of light and multiply it by 0.99, that's what you get. Now, for our gamma value, we need to plug that in. So we get 1 over square root 1 minus, so v squared, 2.97 squared over 3 squared. Okay, because they've both got the same factor. And what do we get? So 7.1 overall. That sounds about right, actually. Okay, so 0.99 times 3. Don't mind me just working this out. Not that I don't trust you guys. So 1 minus that. Square root of over that. 1 over that. Yep, you're right. 7.1. Sorry for doubting you, not that I ever did. So our Lorentz factor is 7.1. So our momentum, using this formula right here, we can work out our momentum because now we have our Lorentz factor. So our momentum is going to be equal to 7.1 multiplied by the mass, which is 1,000, multiplied by our velocity, which is 2.97 times 10 to the power of 8. Let's work that out. 7.1 times 1,000 times 2.97 times 10 to the power of 8. And hopefully you get about 2.1 times 10 to the power of 12. Kilogram meters per second. Hopefully you guys remember the units for momentum. Okay, remember mass times velocity, so kilograms times meters per second. So there is our momentum of our spaceship. 2.1 times 10 to the power of 12 kilogram meters per second. Okay, so if you're a stationary observer, that is what you would observe the momentum of that spaceship being. So now, here's the really interesting bit. We want to apply, twice the momentum we found in part A. Okay, so if we take twice that momentum, we apply it to our stationary rocket, calculate the new final speed of the rocket in terms of c. Okay, so we want to take twice this momentum, apply it to our rocket, and see what our velocity is going to be. So, first of all, twice that momentum. So momentum is going to be 4.2 times 10 to the 12. Okay, I just doubled that, because that's what we're doing here. Sorry, I just need to get that equation back. There it is. Okay, so that equation, to work out velocity given momentum, our velocity is equal to P over M square root 1 plus P squared over M squared C squared. That's how we're going to find our velocity of this spaceship. We know our momentum, we know our mass, and we know the speed of light. Okay, so let's start working this out. Now this is where we need some fancy calculator skills. So, P squared, yes? Oh, is it? Oh, that's a shame. Can't square the momentum, really? Okay, that's problematic. You'll have to take my word for this for now, and we'll have to see what we can do about it. Okay. Oh, that's a good point. Sorry? Yeah, well, that's what I was planning on doing. Well, let's give it a go. So, P squared. Oh, yeah, that's what you're saying. You can't do that.
You need to use the square so you can cancel it.
Yeah, you can cancel stuff out, but I'd rather not do that because I make mistakes that way. I don't know about you guys. Yes.
Instead of kilogram meter per second, can you do tons meter per second? So I can.
You can? Okay. All right, cool. Might have to ask you how to do that in a second. Instead of kilogram meters per second, can you do... You can do Newton seconds. Oh, okay, I see what you're saying. Some of us will work... All right, hang on. Let's just work this out. We'll work out the problem afterwards. So 1,000 squared... Oops. 1,000 squared times c squared. Okay. Forgot to square my momentum. So I am recording this, so obviously there's long silences are going to be great to watch later.
Yay.
Okay. So I get that to be 197 square root of that. Hang on. 7 times 1,000. And momentum divided by that. Hang on. Okay. If you can work it out step by step, which I've just done, you should get something about right, which is I get 2.99 times 10 to the 8 for our V. And now, if we work this out, so we want it in terms of C. Okay? You have to take my word for it. This is equal to this. If you can't get that yourself, we'll work on it later. But we need to get this in terms of C. All right? So let's just work it out as a percentage. So our answer here divided by 3 times 10 to the 8. Oops, hang on. 2.99 divided by 3. And I get our velocity is equal to 0.997 c. Now, This is the point of this problem. We started off with this momentum here. Our rocket was travelling at 99% of the speed of light, okay, 0.99 times c. If we double this momentum, this is an enormous number. If we double it, it becomes an even more enormous number. But look how tiny the change in that velocity is. Instead of 0.99 times the speed of light, went up to 0.997. And so the closer you get to the speed of light, the less your changes have any effect. Doubling this momentum has only increased our speed by 7 1,000ths of what it was before. Okay, that's the problem with relativistic momentum.